Okay, so I want to talk about some other classification methods. This one, I haven't found like a good textbook online that covers the Bayes classifier and also the naive Bayes classifier. All right. This is a probabilistic classifier. In that the output will be the probability that an observation belongs to a certain class. Okay, and even though it says Bayes classifier and naive Bayes classifier, this is not a Bayesian statistics method. Okay, it uses Bayes' rule, but it's not a Bayesian statistics method. And so we'll spend some time talking about Bayesian statistics, but despite its name, it is not you could apply Bayesian statistics principles to it, but in its base form, it's not. Okay, it's not a Bayesian statistics method. It gets its name from Bayes' rule. Okay, which is also where Bayesian statistics gets its name, but the name comes from Bayes' rule. All right. Okay, so this is the result of the classifier. You're going to get a probability all right, so let me go explain the notation of each of these pieces here. Okay, so this is T is going to be the kind of the class. All right, so the class T of a new observation belonging to class C. Okay, so this first part is the probability that a new observation has the or belongs to class C. Okay, and over here, this is given the inputs or the predictor variables have the values in the vector x new. Okay, so given the predictor variables have the values in x new, and also given our training data. Okay, the training data consists of predictor variables x in a matrix and class assignments vector t. Okay, and this will be a vector of probabilities, okay, corresponding to each class. Okay, and so this vector, the vector adds to 1. So if there's 3 classes, you know, this vector pi c will be like 0.6, 0.3, 0.1 or something. 60% class 1, 30% class 2, 10% class 3, or something like that. Okay. So yeah, maybe I'll just say the sum of the pi classes from c equals 1 to k will equal 1. Okay. And you know, our training data, I don't know, will be predictors x and known classes t. You might have x1, x2, x3, and then some vector t. Okay, just 4, 5. I don't know. These might belong to class 1, and then x2 if you have class 19, 18, and 19, and 17, and 16. Maybe these belong to class 2 or something, right? And if we have a new observation, so, sorry, this over here would be, this is your matrix X, and then this over here is your vector T. Okay, so 4, 4, 5 is class 1, 5, 5, 4 is class 1, and you have 20, 18, 17, that's class 2, 19, 19, 16 is class 2. All right, and then so you have X new, and maybe it has the values 5, 4, and 4, and then the question is which class does it belong to? Okay, all right, and then so we would say, you know, we would guess class 1, right? And so our result would probably be something like this. Pi of c will be, I don't know, 0.96 versus 0.04. We'll say class 1 versus class 2. So this is just a fictional result. And that's how we do it. Okay, so we say based on the training data X, okay, our known labels T, if we are given a new X value, okay, I guess I can put a vector here, okay, because our new X values are 5, 4, 4. Based on that, what are the probabilities that the T belongs to class C, and you would have to produce, you know, the Bayes classifier would produce values like 0.96 and 0.04. Okay, and you know, this was just a simple example that we're looking at in our head, but basically, you know, our brains are kind of interpolating or whatever we're doing. We're saying, oh, 4s and 5s that look like class 1, and numbers around 19 look like they're class 2 or something like that, right? Okay. So how does this work? All right. Well, we're going to use Bayes' rule. All right? And I don't know if you guys remember your probability notation. This is the probability of event A given event B. Okay, and Bayes' rule says that the probability of A given B is equal the probability of B given A times the probability of A divided by the probability of B. So if you want to know what's the probability of A happening given that B has happened, okay, you can do these calculations and say, you know, what's the probability of A? You multiply that by the probability of B happening, given that A has happened, and you divide that by the probability of B, and this is how we can calculate this, okay? So, this is what we're going to do. We want the probability of tau t nu equal to class C given our vector x nu and given our matrix X and our vector T. So using Bayes' rule and letting this kind of be the A and this kind of being the B, all right, x nu, this is going to be the probability of x nu given t nu equal to C and our training data multiplied by the probability of A, or the t nu equals C given our training data, divided by the probability of x nu given our training data. Is that okay? So if just only really just look at this part as A and this part as the B, okay? And then everything we're doing is based on the training data that we have, so that part's always going to be in the given part. But if you do that, then, you know, B and A and A and B, something like that, okay? All right, so let me just kind of break down each part, okay? So each component. All right, let's talk about what this means. The probability of x nu given t nu, and so this is going to be the probability of observing the values in the vector x nu. If we pretend or imagine, or if we suppose that that the observation belongs to class C. I guess I'll just, if we pretend the observation belongs to class C. So it's saying, you know, if we pretend that this observation belongs to class C, that is t nu equals C, you know, what are the probabilities of getting the values that that we've observed? Okay, because right now what we're doing is we've observed these values and we want to figure out which class it belongs to. But we're going to say, all right, let's flip this around and let's just say, let's pretend it belongs to this class. What's the probability of getting these values? Okay. But we don't want to just say, oh, the probability of getting these values is this, therefore our result is this, because the there could be a kind of uneven proportions of classes. Okay, so so we want to know, what are the, without looking at anything else about the thing, just kind of looking at the training data only. This is the probability that a new observation belongs to class C, okay? If we know nothing else about it. Okay, so, the probability that a new observation belongs to class C if we know nothing else about the observation, and all we know are and the only thing we do know are kind of what values we have in our training data. Okay. And then in the denominator, we have the probability of x new given our training data. Okay, this is just the probability of observing these values in x new given our training data. Now, this is actually, this can be a complicated value to find. And its purpose, the reason why we have to include it, is so that our resulting vector will add up to 1. Okay? It's kind of, if we only had the numerator, the resulting vector is not going to be guaranteed to add up to 1. By including this denominator, it's going to just kind of multiply it by something so that the resulting vector will add up to 1. Okay? Its purpose is to ensure that when you add up the resulting probabilities, you're going to get 1. Okay? So basically, if you just take the numerator and add them up, that's going to be the value of the denominator. Okay? Because so if the numerator adds up to 6, then the denominator is going to be 6. If the numerator adds up to 0.2, then the denominator will add up will be 0.2. And that way, after you divide the numerator values by the denominator, the resulting values will add up to 1. Okay, so probability of x new given your training data will equal to the sum of the numerator values. Okay. So, is that okay? Do you want me to write this out, or some of the numerators in this thing? So you're just going to take the numerator and you're going to calculate it for each class. Here, I'll say it'll be the sum of the numerators, calculated for each class. Okay. All right, here is a silly example. All right, I was looking up, all right, the largest land mammal. All right, do you guys know what this is? It's an elephant, and specifically, it is the African bush elephant, okay? All right. All right, so the African bush elephant is our largest land mammal. And okay, and we will say the male weight is has a mean equal to 13,000 pounds, and I made up the standard deviation numbers because I couldn't find standard deviations of elephant weights, but I just arbitrarily said 2,500 pounds. Okay, and then female weight, I didn't realize there was such a drastic difference, but the female weight has an average of around 6,600 pounds with a standard deviation of 1,100 pounds, okay? And I'm making up this part. All right, all of the, okay, so basically the only things that are like facts that I kind of looked up on Google are the 13,000, 6,600. Everything else I'm making up just for the sake of our problem. Okay, but we'll say females are more common. I don't know. And we'll say, let's say the population is 70% female and 30% male. Okay. So, so this part, we will say these summary statistics are based on the training data. So we're going to pretend that, you know, we had training data, and based on our training data, you know, in our training data we had males and we had females, and in our training data 70% were female and 30% were female, or 30% were male, and the mean weight of our training data males, there's 13,000, and standard deviation is this. Okay, so we're going to pretend that these summary statistics are based on our training data. Is that okay? All right. And so let's say we observe a new elephant. So we only have one input here. Okay, we get a new elephant. And the weight is 9,000 pounds. Now you have to guess. Do you think this is a male elephant or a female elephant? All right, I purposely chose a hard to tell one, right? Okay. So we'll ask, what is the probability the elephant is male versus female? Okay. Right, and so we say, well, you know, maybe it's a heavy female, maybe it's a lightweight male. We got to kind of compare its relative probabilities, and then, and we also won't have to take into account that females are more common. Okay. So, how does this work? Okay. So, so before I told you anything about the elephant, yeah, question.
Are we assuming that females are more common in the population? So if we're drawing in a new observation, that would be the type of ratio we would expect, or is this simply a factor of our data? Okay,
yeah, that's a good question. I guess I should say our data is 70% female and 30% male, and we're assuming it's a random sample. and so we're projecting this onto the population. And maybe I should write, I'll write, based on our data, we assume the population is 70% female and 30% male. That's a good question. Okay, so based on data, we assume the population is 70% female and 30% male. Okay, so that's what we'll do. And so now I'm going to, so we have this thing. All right, so if we know nothing about the weight, kind of, we would say the probability that T nu is female, given kind of our training data, would be 0.7, right? So the probability that T nu would be female, given our training data, is 0.7, okay? And then, and thus the probability of T nu being male, given our data, is going to be 0.3. Okay, and now we want to know, so that's one part of our numerator, okay? So part of our numerator is this T nu equal to a class given our data. The other part of our numerator is probability of X nu given T nu, all right? So we're going to pretend, so that's the part of our numerator. The other part is the probability of X nu given T nu equals our class and our data. This is going to be, all right, so we will pretend, okay, if we pretend the observation is female, what is the probability X nu equals, what is it? 9,000, okay? Okay, so this is going to be, what's the probability that X equals 9,000 given that T nu is female and, you know, whatever our data says, okay? So we have to start making assumptions, and maybe one assumption will be that our data comes from a normal model, okay, with this mean and standard deviation. Okay, so we'll say as assume the probability of X given the class, you know, follows a normal model. So this will become so we'll use the normal PDF. So the normal density function. And I don't know, we have a few options for this. We can convert to z-scores, or we can just use R's function for the normal density. Is that okay? So normal PDF, so I'm going to just use R's dnorm function. And I'm going to say R dnorm of 9,000 given that the mean, and for females the mean is 6,600 and the standard deviation, what did I say, is 1,100? Again, with my made-up statistics here, okay? And all right, let's go to R and we'll say dnorm. So this is the probability of 9,000 given that the mean is 6,600 and the standard deviation is 1,100. Okay, I get 3.356 times 10 to the minus 5. So this is equal to 3.356 So there's a small density there, okay? Density is not the, yeah, okay, so that's what we have there, all right? So if we pretend the observation's female, this is what we get, okay? And likewise, if we pretend male, it is male, what do we get? We'll say the probability of getting 9,000 pounds, given if we assume it is male, okay, this will be d norm 9,000. The mean is what, 13,000, and standard deviation is 2,500. Okay, so I'll go to R and I'll ask for this. 9,000 mean is 13,000, standard deviation is 2,500. Okay, and I get 4.437 times 10 to the minus 5. Okay. So the likelihood of our data, they're both on the order of 10 to the minus 5, but according to this, it's more likely, based on the weight alone, it's more likely to be male than female, if females and males were equally represented in the population, okay? But now we have to factor in the fact that when we randomly select someone or select an elephant, there's a greater chance that the one we're randomly selecting is female, okay? So, okay, so the sum of the numerators. Okay, so the numerator is the probability of x nu given t nu and x and t multiplied by the probability of t nu given x and t. All right, so we'll do it for the female. We have 3.356 times 10 to the minus 5 multiplied by 0.7, which gives me something, okay? And then for the male, we have 4.437 times 10 to the minus 5 times 0.3, okay? And this gives me something. You know what? I have the calculator here. Okay, so we'll do this, and I do dot last value times 0.7. Okay, I get 2.349 times 10 to the minus 5. And then over here, I'll do this. Okay, dot last value times 0.3. I get 1.331 times 10 to the minus 5. Okay, and yeah, this sucks. Okay, so I've got this times 0.3 plus this times 0.7. So the numerators summed up give me 3.680 times 10 to the minus 5. So this is going to be our denominator. The denominator is equal to the numerators summed up for all classes. Okay. All right. So basically, I just have to normalize these values. So then the probability for females will be 2.349 divided by 3.68. I mean, I can multiply by 10 to the minus 5, but they're going to cancel out, right? So 2.349 divided by 3.68, okay, I get 64%. And that means the male is going to have to be 36%, but this will be 1.331 divided by 3.68, and that'll give me 36%. Is this okay? This is the Bayes classifier, all right? And the way it works is just, the numerators, we just kind of factor in, if we pretend it belongs to this class, how likely are we to get this value, right? And maybe it's very likely, maybe it's very unlikely, okay? And then we do that for every class. We just say, if we pretend it's this class, how likely is it to get this value? And then, but we weight that likelihood of that value by kind of the class probability. So, certain classes might be more likely than other classes, and so we weight them accordingly. And that's what we do, okay? And yeah, the denominator just serves, its purpose is so that when you figure out the numerators, they all add up to 1, okay? That's the Bayes classifier. Yes?
So, is there a way of summarizing, like when I look at the output from this?
Yeah.
It seems like you're mostly sticking to what the sample mean was. Is that because intuitively, if you look at the probabilities, if you assume that the distribution is normal, that it's like really unlikely to be either male or female individually with that particular?
It is like individually, like according to the model, it says it's unlikely to find a elephant that's 9,000 pounds. It's kind of like it's like too big to be female or too small to be male, but we're saying there is an elephant here, and we haven't, just on that weight alone, can you guess? That's all we're doing, okay? We don't actually care, like, this is the overall probability. This thing is, where'd it go? This is the probability of x nu given our data. So given our data, we're saying it's very unlikely that we get an elephant that's 9,000 pounds. That's what this says, okay? This is the total probability of getting an elephant that's 9,000 pounds. So this is very unlikely. But we don't actually care about that. We're just saying, if I have this 9,000 pound elephant, give me a class prediction, okay? Tell me, can you make a guess if it's going to be male or female? And our answer is, you know what, we think it's going to be female, because females are more likely overall, and the relative probability of this value is not that big of a difference there. Yeah.
I guess what I'm asking is it just a coincidence that the 0.64 is very close to, like, if you just blindly guessed, it's probably 70%.
No, it's not. That's a coincidence of this 9,000 pound, because I purposely picked a value that's kind of in between. Here, let's just try another example, right? So if x nu were 13,000 pounds, okay? X nu is 13,000 pounds. Like, just because you've seen this data, you already know that it's very likely to be a male elephant, right? Because, but if we did the calculations, okay, so the probability that T is going to be female, given the data, this is still 0.7. The probability that T is male, given the data, this is still 0.3, okay? But then we ask, what's the probability of getting X is 13,000 if the elephant is male? So this is going to be D norm of 13,000 if the mean is 13,000. and the standard deviation is 2,500. Okay, that's going to be like 0.398. I don't know what it is. Okay, d norm 13,000 divided by mean. It's not going to be that. It's going to be a small value because the mean is standard deviation is so big. 2,500. Okay. Okay, so I have. I don't know what this is. 0.000159. Okay, that's fine. 0.000159. Okay, so that's that. Meanwhile, we have probability that x is 13,000 given if we pretend this observation is female. So this is going to be d norm 13,000. Mean is 6,600. Standard deviation is 1,100, right? So what is 13,000 minus 6,600 is like 6,400, and standard deviation 1,100. We're like 5 something standard deviations away, right? So 13,000 minus 6,600 divided by 1,100. Yeah, we're 5.8 standard deviations away, which is a ridiculous number of standard deviations to be away. But let's just see what the R has to say about this. Okay, so we say the mean is 6,600. The standard deviation is 1,100. Okay, so it's on the order of 10 to the negative 11, right? 1.617 times 10 to the negative 11. Okay, which is like practically 0. Okay, it's not 0, but it's practically 0. Okay, so then if we calculate the numerators, right, for a female, we've got 1.617 times 10 to the negative 11 times 0.3, and we're going to get, I don't know, 4.8 times 10 to the negative 12, right? Oh, 0.7. Okay. So even, what's happening? Okay, 0.7. All right, what is that? 1.6 times 0.7. Okay, 1.12 times 10 to the negative 12. Or 10 to the negative 11. So not. And then for the male, it's going to be, I don't know, whatever this is. 1.596 times 10 to the 1, 2, 3, 4. 10 to the minus 4 times 0.3. Okay, and we get 4.788 times 10 to the minus 5. Okay, and then, if these things have to add up to 1, this is going to be like 0.9999 something, and this is going to become 0.0001 if you normalize these by its thing, right? So this just kind of confirms it. And so it says, even though if we pick an elephant at random, it's more likely to be female, it's even less likely that it's a female that weighs this much, okay? And because it's so unlikely that a female weighs this much, that's going to counteract anything else. Even if the population was extreme, where it was like 99% are female and 1% are male, okay? This is the difference in the likelihoods are 7 orders of magnitude apart. Okay, so the difference between 99% and 1% is still going to get drowned out by the difference in the likelihood of the numbers. Okay, whereas if you're in a situation where you're kind of in between, which is in our first situation where the 9,000 pounds is kind of this ambiguous, you're not quite sure if it's a heavier elephant female or a lower weight male, the original class probabilities of 70 versus 30%, that factors in a lot more, okay? And so we're saying it's, the fact that the original population we're assuming to be 70%, that's going to weigh a lot heavier, okay? And so the Bayes classifier kind of blends the likelihood of your data along with the class probabilities that we're assuming without looking at the data. This can be extended to multivariate applications, okay? Okay, so in the above circumstance, we only had you know, one x variable, but you know, it could be x1 and x2. Maybe this come from a multivariate normal distribution. All right. And in a multivariate normal distribution looks might look something like this. Okay, where if you make a projection onto one of the axes, you get a normal distribution, and if you make a projection onto the other axis, you get a normal distribution. But you know, maybe there is covariance. There might be some covariance. So each variable by itself is normal. There could be covariance between the terms. Okay, there could be covariance between the terms. And we would say x1 and x2 come from a normal distribution, and you would have a mu1 and a mu2 and a standard deviation of sigma 1 squared, sigma 1 2 covariance. This is probably too much. So this is kind of your covariance matrix, your variance covariance matrix. Okay. If there's no covariance, between x1 and x2, then you would have kind of the if you were to draw like axes through the ellipse, they would be perpendicular. Okay, you still have a normal distribution over here and a normal distribution over there. Okay. Kind of indicating that, you know, even though for large values of x1, you know, x2 is not influenced, and you know, for large or small values of x2, x1 is not influenced either. You still have normal values, and you know, here I purposely drew it flat rather than a circle to indicate you can have different sized variances. So like one normal distribution could be more pointy than the other. They're still normal, and they're still there's no covariance between the two. Okay. Anyway, the Bayesian classifier still works the same way. Okay, So the resulting probability of your class given your x new values and the training data is going to equal basically the density of the x new values according to the multivariate distribution, multivariate normal distribution, okay, multiplied by the class probabilities according to the data, divided by the sum of all the numerators for every possible class. Okay, and basically we would use our training data to estimate the parameters of the multivariate normal distributions for each of the classes. Okay, so you'd probably filter out everything, all of your observations that belong to class 1, and then you would, find the mean to get your mean vector for class 1, and then you'd have to calculate your covariance matrix for class 1 and class 2, and that would be probably your the values that you're going to use to estimate the parameters of the the multivariate normal distribution for class 1. Okay, and then you do the same thing for class 2, and that's how you would then estimate the density of x new. It's 8:40. Oh shoot. Okay. So anyway, all right. So the steps would be something like filter to class equals 1. Estimate the mean and variance covariance matrix and variance covariance matrix using your data. Okay. Do the same for covariance matrix, I would say, of class 1 using your data. Do the same for each of the other classes. Okay, and then calculate based on your estimated distributions, calculate the numerators. I gotta work quickly. I think I can squeeze it all in there. All right, so this is Bayesian classification for multivariate stuff. Okay, we have what's called the naive Bayes classifier. All right, which is a modification of this multivariate Bayesian thing. All right, and the reason why we call it naive Bayes is because we are just going to assume each x variable is independent of the others. This might be a bad assumption, okay? The naive Bayes classifier, okay? We assume the x variables are independent of each other. Now, why would we do this? Okay, well, estimating the variance-covariance matrix for each class requires a decent amount of data, okay? Like, in order to estimate to get a good estimate of the variance-covariance matrix, we need a lot of data. And if we only have a few data points, the estimate of our variance-covariance matrix could be very wrong and end up produce bad predictions here, okay, or bad density estimates, okay? So here I'll say, in the non-naive model, we need to estimate covariance terms. And if we do not have enough data, our covariance estimates could be bad. All right. In the naive model, we're going to just say all the covariances are 0, okay? And so they're not going to be good estimates at all. But you know what? It turns out it's okay. So in the naive model, we just say all the covariances are 0. Okay, and this then the joint distribution of all the x variables just ends up being the product of each probability, okay? Because if random variables are independent, then you can just multiply their probabilities, okay? So it also simplifies our computations. We don't have to worry about this crazy multivariate distribution. The joint distribution of all the x variables become the products of univariate distributions. So, you know, the probability of x new taking on the value, you know, x1 and x2, given the t new class in our training data, just will become, you know, the probability that, you know, x1 is equal to your x1 given the class and the training data times the probability that x2 equals your x2 value given the class and your training data. So this is the fact that we just multiply the univariate probabilities together is the naive assumption. Because there could be a covariance term that we have to worry about, but in a lot of circumstances, it's okay to make this naive assumption and just multiply them together. All I have like 2 minutes left. I might go over 2 minutes. The last thing I want to talk about is K nearest neighbors classification, okay? We'll get this all in there, okay? K and N shows up for a lot of things, okay? And basically, you have some data points, okay, that belong to, maybe here I have 2 different classes here, okay? I've got red. Here, you can do, if you only have one color pen, you can do dots and X's, okay? So K nearest neighbors classification, you have to have some kind of distance metric, right? So how do we measure distance? Okay, so generally we'll use Euclidean distance, so distance metric, usually Euclidean. Okay, which will be basically the square root of, you know, x1 minus x2 squared plus y1 minus y2 squared. Okay. And you have a new point. This is your new point, okay? And the way it works is you have K, which is some arbitrary number. K is an arbitrary number, generally an odd number. And you will measure the distance from your new point to every other point. Every other point in the data set. I guess I should say in the training data. So you measure the distance from the new point to every other point in the training data, and then you sort them from least to greatest. Okay? And then your top K rows are your K nearest neighbors. Okay. So one thing about K nearest neighbors is all of your predictors have to be numeric. Okay. You can't have categorical because you need a way to measure distance, right? You can't measure distance from red to green. Okay. You need like 5 and 7, and you can say, oh, there's a distance of 2 or something like that. Okay. So so the top rows are your the top K rows are your K nearest neighbors. And then basically each neighbor, each of the K nearest neighbors, K and N, get a vote for their class. Okay, and then majority wins. So if this is my new observation right here, and I say, what are my 3 nearest neighbors? I say, okay, well, actually, I don't know. So this is probably my closest one, and this is probably my second closest one, and which one's is this the third closest one? I don't know. All right. So you would need a thing and to, okay, well, let's just do our 5 closest neighbors because that seems to be, so this is, we'll say this is 4, and this will be 5, okay? And each one, it's not that the nearest one gets a bigger vote or whatever, it's just, we have our 5 nearest neighbors. So these are the 5 nearest neighbors. Where did my cursor go? Okay. So these are my 5 nearest neighbors. Okay. 3 are blue to our red, okay? So x new will be classified as blue. And that's it, okay? In some circumstances, you might have a tie, and then you'll need something to do like a tiebreaker. Generally, you'll do your one nearest neighbor will break a tie. Okay, so if there is a tie, there's a common strategy, and I don't want to say this is the only way to go. A common strategy is to use the nearest neighbor as a tiebreaker. Okay, but if you only have two classes and you pick K to be odd, you won't run into this issue. But if you have three classes, it's possible to have like 4 and 4 and 1 or something like that, even with an odd thing, and then you'll need something to break your tie. But that's it's a very simple algorithm. It shows up a lot if you've got just a whole bunch of numeric things. They've expanded it and made it a lot more complex to make it, I don't know, work in different kinds of situations. Some of the things that you might consider doing, okay, is, if x1 and x2 are on different scales, right? Because it doesn't know, like if x1 has a range of like 0 to 1 million, and then x2 has a range of like 2 to 7, okay, then x1 is going to like dominate all of the distance metrics. So it might make sense to like normalize them, so everything's kind of on the same scale, things like that. There's different things you can do to enhance k nearest neighbors, but the overall algorithm is very simple, right? Just find your new point, calculate your distance to every other point just using Euclidean distance, and then sort them from least to greatest. And the thing about Euclidean distance is that it generalizes to higher dimensional space. You just take the difference between x1 and x2, square it, y1 and y2, square it, z and z2, square it, and w and w2, square that. So it generalizes to high dimensional space and things like that. Okay, we covered a lot today. It's your favorite thing. I'll release another homework assignment soon, and covering our lecture stuff. So we'll see you guys next week, and then next week we got 2 lectures that week. So it's fun. Oh, we forgot attendance. Oh, shoot. Okay. Is anybody not